For this second problem, you actually need a graph, and the graph is going to look something like this. So we're going to have y-axis and x-axis. So this is going to be 30, 20, and 10. And then our function is going to look something like this. That was not what I wanted at all. And about here is going to be 1. Okay, one of the things that you need to know is that we have this dashed line at 30, so our graph never touches it here. So that's the graph that we're going to be using. So the function f has derivatives of all orders for all real values of x. Let p sub n of x represent the nth degree Taylor polynomial for f at x equals 1. Show that the absolute value of f of 1/2 minus p sub 3 of 1/2 is less than 1/12. So some things that we want to remind ourselves, this right here is equal to the absolute value of r sub n of x. And in our case, n is going to be 3, x is going to be 1/2. So we are doing our absolute value again. So r sub n of x is less than or equal to the absolute value of x minus c to the n plus 1 divided by n plus 1 factorial times the max of f of n plus 1 of z. We are going to have c, n, x, and then the max that we want. We said n is 3 because p sub n is 3. We are doing it of 1/2, so I know x has to be of 1/2. And it said for f at x equals 1, so that means our center is 1. For our max here, we're going to be looking at this graph, and the maximum that we are going to be picking is going to be the biggest possible thing within reason. So we can see that we never go above 30 with that line. So we're going to pick 30 as our maximum here. Now I could try to pick something smaller than 30, like 29. It probably doesn't hit 29, but because we can't tell for sure with our graph, 30 is our best option. So we have r sub 3 of 1/2 is less than or equal to the absolute value of 1/2 minus 1 to the 3 plus 1 divided by 3 plus 1 factorial times our max of 30. So just like before, we're going to go ahead and plug it in to something. It could be a calculator, it might not be. So we do have to be a little bit careful of that. Things that I know, 1/2 minus 1 is, and absolute value is 1/2. 1/2 to the 4th power is the same thing as 1 over 2 to the 4th power. We have 4 factorial. So we're going to be dividing whatever it is by 24. So we have right now 1/2 to the 4th power. So 2 times 2 times 2 times 2. So 2, 4, 8, 16. So we have 1 over 16. 1/16 divided by 24 times 30. So we have 30 over 16 divided by 24. If we do some moving around, we're going to eventually get 5/64. If you put it into the calculator, you're going to get a decimal that is this. So we're looking at that 5/64. And we want to decide if this 5/64 is less than 1/12. So 5/64 and 1/12. I don't know about you, but I don't know if I would necessarily be convinced. So one of the things that we might do is change 1/12 to look more like what we have. So what I might do is I might multiply the top and the bottom of 1/12 by 5, so I have 5 over something. If 64 is bigger than what we get, then we know that we have not shown what we want to show. If it's less than 64, then we have shown it. So if I multiply 1/12 by 5, we get 5 over 5 times 12 is 60. 5/60 is going to be bigger than 5/64 because we're dividing 5 up into less pieces, so we know that we are good to go. The big thing here is we want to make sure that at the end of this problem we make some claim that whatever we got is less than 1/12, and we want to make that claim because otherwise we haven't actually shown what it wants us to show. Use a second-degree Maclaurin polynomial for cosine to find the maximum error of an approximation of cosine of 0.03. So we need our C, N, X, and max. It's a Maclaurin polynomial, so we know that it's 0. It says a second degree, so we want to know N is 2. We're approximating cosine of 0.3, so 0.3 is X. And our maximum, we're dealing with a cosine function, so the maximum value cosine is going to be, or sine is going to be 1. So we have the absolute value of R sub 2 of 0.3, and that's less than or equal to absolute value of 0.3 minus 1 to the 2 plus 1 power. 2 plus 1 is 3, so I'm going to go ahead and just put 3. Divided by 2 plus 1 is 3 again, so we have 3 factorial times 1. So we have that this is equal to 0.3 minus 0 is still 0.3. 0.3 is the same thing as 3/10, so I have 3/10 cubed. 3 factorial is 6, and times 1 doesn't matter anymore. 3 cubed is going to equal 27 over 1,000. And we're dividing that by 6. If we multiply by the reciprocal, we're going to get 27 over 1,000 times 1/6, because right now it's 6 over 1. If I can kind of get rid of something they have in common, 27 and 6 are both multiples of 3, so I can factor out a 3. This would give us, instead of 27, we have 9 over 1,000 times 1 over 2. So this would equal 9 over 2,000. If they let us use a calculator, that's going to equal 0.0045. So we didn't have to do a ridiculous amount of stuff. We just had to know the formula and then plug in what we know to kind of find this answer. So our maximum error is going to be 9/2000ths. And then this last one here, estimate e to the 1.3 power using a Taylor polynomial about x equals 1. What is the least degree of the polynomial that assures an error smaller than 0.001? So this is kind of using what we know, but in a separate way. So we want our error to be smaller than 0.01. So instead of taking what we would normally do, our equation, and plugging everything in, we want this remainder, 0.001, to be bigger than that absolute value of x minus c to the n plus 1 of n plus 1 factorial times our maximum. So we're going to pull some information from this problem. We need c, n, x, and our max. So we know c is going to be 1 because it's a Taylor polynomial about x equals 1. N says that that's what we're looking for, so we need to find that. We are looking for e to the 1.3, so 1.3 is going to be our value here. And we are estimating e to the 1.3, so e to the 1.3 is going to be our max for this problem. So we're going to use e to the 1.3 to be that maximum that we would need to multiply by it. We can do that because e to the power is going to stay as that maximum because that's that same derivative, e to a power. So we're just going to use that as the largest thing that we could go off of. And this is where that overestimating comes in, but we're overestimating in a smart way. So now what we're going to do is we are going to try to move some stuff, like plug stuff in and then move some stuff around. 0.001 is less than, or is bigger than our x value of 1.3 minus 1. We don't know what n is, so we have to keep these n plus 1s. And then our maximum is going to be e to the 1.3. The first thing that we're going to do is divide e to the 1.3 on both sides. This is going to give me 0.000273. From here, we're going to be using guess and check to kind of decide what values make the most sense. And we don't normally use guess and check very often, but we're going to use it here. The reason why is that n factorial piece makes it really hard to come up with a algebraic way to solve for it. So for what we're doing, guess and check is going to be the fastest way to do this. So we need to remember that n has to be positive whole numbers. So 1, 2, 3, 4, 5, and so on are going to be what we want. We also want the least degree polynomial, so we need to check at least 2 numbers because we need one that works and one that doesn't, so that way we can kind of see which one is good for us. So one of the things that we may do is if I look here, I might kind of guess and check without writing some stuff down. So if I plug in, say, 1, 1 plus 1 is 2, so if I subtract these, we have 0.3 squared, or 0.3 times 0.3. This is going to be 0.09, and we are dividing that by 2, so we're dividing it in half. I can already tell that this is not enough zeros to match this piece over here. If I do that to the second power, meaning that I'm cubing that, 0.3 cubed is going to be 0.0027, I believe. Nope, just 0.027. So if I divide that value by 3 factorial, which would be 6, we're going to get 0.0045, and still not enough zeros. So the first one that I'm going to actually write down is n equals 3. So we have n equals 3. For n equals 3, we want to make sure that 0.000273, that this is a true statement. So we have 1.3 minus 1 to the 3 plus 1 divided by 3 plus 1 factorial. So this right here, we have 1.3 minus, so we're going to have 1.3 minus 1, which is 0.3, and we're going to raise that to the 4th power. So 0.3 to the 4th power gives us 0.0081, and we're dividing this by 4 factorial. 4 factorial, 4 times 3 times 2 times 1, which would be 24, is going to give us 0.00033375. We have the right amount of zeros this time, but that first number, 3, is bigger than 2, so I know that these are not going to work. On the other hand, if we look at n equaling 4, for our same thing, we're looking at 0.3 to the 5th power, and we are going to be dividing that by 120. This gives us 0.00002025. This has one more zero, so we know this is true, which means that the largest possible degree, or the smallest possible degree, to get an error of that 0.001 would be the 4th degree.